Okay, hopefully everyone is okay. And today, our objective is to go through section 3.1 of the book, which is at the start of continuous random variables. And in particular, we'll go through the notion of probability density functions for continuous random variables. Okay, now, if we have time at the end, I will go through question 2.4.3 in the book. Okay, I will go through 2.4.3, 2.43 of the book, problem. This was what I wanted to go through last time, but I didn't manage to, but it's okay. It's optional anyway. As long as we get to finish probability density functions, we are okay in terms of pace. All right. If you are in the lecture theater, you can collect your paper. If you are not in the lecture theater, you cannot collect, obviously. But it's okay, anytime you want. And David, you don't need to walk down right now. We can do it during the break, okay? Right. So now we are going to talk about continuous random variables. And I will abbreviate continuous as CTS, so we don't have to write so much. Continuous random variables. This is the start of chapter 3, which will take us another 3-4 weeks. Okay, let's do it slowly. All right. So we are going to focus on continuous random variables. And so the motivation is the following. Up till now, we have only modeled random variables, that is outcomes, as discrete objects. So what we have done up to now, all our probability models have been involving, for example, coin tosses, in which we observe heads or tails, or sequences of heads and sequences of tails, or dice throws 1 to 6, like in the quiz, or for example, what else have we done? Cards, right? So Liao Xuan, you need to know that this card, right? 52 cards inside, there are 4 aces. I don't know how many aces you put down, but whatever is fine. All right, because knowing how to do the question is more important than its prior knowledge. But these are discrete outcomes, right? So there are 4 heads, 4 aces out of 52 cards, 4 jacks, you know, all these things. Right. So, however, sometimes it is more natural for us to model natural phenomenon as continuous random variables. All right. So, for example, natural phenomenon continuous observations. For example, I can actually discretize all your heights, right? From 1.50 to 1.51 to 1.52 and all the way to 2 meters, for example. All right, so there are about 50 steps here, but that would be very unnatural, okay? Because it would be better for me to model that as a continuous random variable or continuous observation, okay? So besides heights, right? So some other natural phenomenon that we can model, we should model using continuous observations, include temperature. All right. Of course, we can say today's temperature is hot, yesterday's was cold, but we may want a more fine-grained calibration of the temperature, or rather, example, speed of a car. Okay, it can be slow, fast, but also you can give a quantitative number like 80 miles an hour, which is super fast, right? Or if you are running, the fastest man can run is about 26 miles an hour. All right, so that is a continuous type of number. Speed of a car, temperature, heights and weights, and so on and so forth. So those are not really discrete in nature. They are discrete after you do something called quantization. That means you split into bins. So it is more natural for us to treat this as continuous random variables. So the book defines, there are many ways to define a continuous random variable. Some of the ways are more mathematically involved than others, but I like the way that the book does it actually. Okay, it is as little mathematics as possible to describe as many things as possible. Okay, a random variable, I don't know whether you remember or not, but a random variable is some function that maps from the sample space to the set of all real numbers. Okay, but I will remind you of this later on. A random variable is called continuous, which I will abbreviate as CTS. If there is a function, there is a non-negative function, which you may have heard of it before, f sub x, and this is called the probability density function. And this is abbreviated as PDF. Okay, probability density function for the probability function of x, or PDF for short, such that the probability that x takes on a certain value, takes on a number in the set B, can be expressed as the integral of f of x, x dx. Okay, so maybe you can put u here, all right, because the variable of integration is u. Now, you may not be so familiar with this in B business, this sort of thing in B. This looks very unnatural. Okay, so, but nevertheless, this is saying that if x is in a certain set, then you can integrate over that subset. But this is a bit abstract, say for some students. Let me make it more concrete later on. Okay, now, so here is for all subsets B of the real line. Okay, now this is very abstract. So let me make it more concrete. Okay, we are actually most of the time interested in intervals only. So for example, if B is this interval AB, this is the set of all x's in the real line such that x is less than equal to A, less than equal to B. So for example, our real line is this. Okay, all the real numbers are on this line here, and this is A, this is B. So my set B is all these numbers from A to B inclusive. Okay, so here, all right, B could be this, in which case the probability is the probability of x taking on the value A to B, which can be expressed as the integral from A to B of fx u du. Okay, so the picture is as follows. As I mentioned, a random variable is nothing but a function that maps from the sample space to the set of all real numbers. Okay, so this is continuous, all right, called a probability density function, all right, and so on. Okay, so the picture is as follows. You have this sample space omega, and you have a certain event. Subsets of the sample space are called events. This event here is the event, for example, that our random variable takes on the value, some value C, that is between A and B. Okay, so that is our interesting event that we want to compute its probability. Now, to every event, say this red event here, a random variable basically assigns, all right, basically you have this, okay, so you map to this particular probability density function. Okay, a probability density function is a non-negative function. We have to first establish that it's a non-negative function. So it could be a very, I'm sorry, I'm trying to draw something nice. Could look like this, fx. And so you have your A and your B here. And basically, if I'm interested in the region on the left-hand side, basically the red region here, then I'm interested in basically the area under the graph here. Okay, the area under the graph. So the integral is the area under the graph here. Okay. Okay. So every event in the sample space is a subset of the sample space for which the random variable takes on certain values, A to B inclusive in this particular example. And how do we compute its probability? We compute the probability that this event happens by taking the integral over this particular region here, this particular interval here, A to B, of this density. Okay, density is short for probability density function or PDF. Sometimes I just say density. Okay, so this sort of things you might or might not have seen before. When I was in school, I saw this before for one random variable. So I don't know whether they still teach this or not nowadays in Poly and JC. Some people might have seen this before. So by the way, this is the PDF or probability density function of X. It is a non-negative function. Okay, it's a non-negative function. And very naturally, it has a few properties. Would you kindly dim the front row lights? Okay, that is more difficult than mathematics. I can do anything to do with mathematics, right? What theorem do I call on? I'm afraid if I... What theorem do I call? Front row lights. I have to do anything, but it's not like this. Here, maybe here, this is the microphone. David, please. Well, but don't turn off my Zoom, okay?
No, it's right here. Yeah, that's it.
Wow, so smart. Okay. Right, thank you very, very much. As long as it's more conducive for everybody, you are good. So you have a particular event on that site in the sample space. That is a sample space. But really, we don't really care so much about the sample space. I just want to tell you that every particular event here, okay, leads to a certain number, and that number corresponds to the area under the PDF. Okay, so that is the punchline of today's lecture, if you can only remember one thing. Now, let us look at some very, very special examples. For example, okay, if A is equal to B, okay, what do you think happens? Now, so for a single value, A in R, that means A is a real number. What is the chance that X is between A and A? Well, this is if and only if X is equal to A, okay? So we can just apply the formula, all right? So probability that X is between A and A, which is the probability that X is exactly equal to A, okay? Is nothing but, okay, here we have integral from A to A of fx of u du, okay? And you know, hopefully that if the limits here are the same, then it is true that this is equal to 0. So the point of the matter here is that the probability of X taking on any single real number for a continuous random variable X is 0. Okay, so this is very much unlike discrete random variables. Now, the probability that if you roll a dice, the probability that X, the outcome of the dice, is equal to 1 is 1/6. So the probability that X takes on a particular value is certainly non-zero for discrete random variables. However, in continuous land, as you can see here, by this simple calculation and by this generic formula, okay, if the continuous random variable is continuous, then such a function known as the PDF exists. And we can certainly use this formula here. And this formula basically says that, okay, if B is set to be A, no one is stopping us from doing that. Then the two limits here are A and A. Now, if the two limits are A and A, then clearly the integral is 0. Okay, this is some basic fact of calculus. So this is one major difference vis-a-vis discrete random variables. Okay, this is a major difference. Discrete random variables. Now, in the discrete land, of course, the probability that X takes on a certain value can very well be non-zero. Okay, so Px of X can be non-zero. And we have seen this many times in many examples in the quizzes, in the homeworks, in the tutorials, and so on and so forth. So here is a certain consequence. This is remark, a math thing. Okay, so we have already computed a probability, or we have found a way to express the probability that X is between A and B inclusive. So it's including the left-hand side and the right-hand side, A and B, because I have this thing here, okay? This means less than or equal to. So we're not precluding the possibility of equal to. This can be written as the sum, X equals to A plus the probability that you exclude A but include B. Can you see that? So X including A and B and everything in between is X equals to A plus everything in between D exclude A. All right. So I think a picture will make this clear. I also cannot do all these things. I cannot visualize this very well. This B, this A. And on the left-hand side, we are interested in everything, all these things, A and B, and everything in between. But this is the same as, well, this green part here, just this part here, together with this purple part here, which is all this stuff together with this. All right. By circling, I mean inclusive. Do you agree with this decomposition? You take the including left-hand side. Now I don't want the left-hand side. I exclude it. I bring it outside, and everything remaining. Okay. This is additive because this has a theorem. This is disjoint from this. All right. Disjoint is not the same as independent. All right. So now we know that this is 0 from the above calculation. The probability that any continuous random variable takes on a certain value is 0. So we are left with only this part here. So the punchline is that actually including or excluding the endpoints A and or B has no effect on the probability. So we have this relationship. Now I include both sides. I've already shown that this is the same as I'm excluding A. All right. By a completely symmetric argument that I'm not going to do, we can see that this is excluding B. Okay. We can exclude B also by a completely symmetric decomposition. I don't want to include B because the probability that X exactly equal to B is 0. Now, nothing is stopping us from also excluding both points. X strictly bigger than A, strictly less than B. So all these 4 things are the same because including any one single point or 2 single points yields 0 probability. It is what it is. Okay. Everyone understand this? So including for continuous random variables, including any one single point is immaterial to the probability, but this is very different from discrete. Discrete, you need to take care of every single point. Okay. Any questions here? Let me see. Call on people. How about Jillian? Everything good? You want to collect your quiz? All right. So we don't really need to include the endpoints to get the same probability. Here's another property of the probability density function, property of PDF. A very natural probability property. Now, clearly we know that X, right, is a real number. So the probability that it is greater than minus, it cannot take on infinity, right? Random variables cannot take on plus minus infinity. So this guy here must be equal to 1 because it includes all the real numbers from minus infinity to infinity, excluding both. All right, the real numbers don't include plus minus infinity. So that is equal to minus infinity to infinity fx of u du. So this must be equal to 1. So the punchline here is that the area under the PDF must equal 1. And that is how we actually figure out some normalizing constants. Now, obviously, there's another property, which is that the PDF must be bigger than 0 for all. This for all, right? Let me write this out in words. For all real numbers U in R. Okay. So these are some properties, some very natural properties. This is called a normalization property, if you wish. The probability density function is normalized. the normalization property, and that is the non-negativity property, if you wish. Okay, non-negativity. Okay. Now, there's something very strange here, okay, that when we compare to the discrete case, there's something very strange about probability density functions. But before I talk about this very strange thing, does anyone have any questions on these properties? These are two properties, property 1 and property 2. Any questions? No questions. Very good. So there are some very strange things that one has to take note of. Okay. Another remark, and that's the following. So we have this thing known as the probability density function. Now, remember or recall that for x discrete random variable, it is characterized, or it has a PMF, probability mass function, Px of x. Okay, so some of the properties are very much analogous to the continuous case. First and foremost, you sum all of them up, you sum up all the probability masses, just as what we have done in the tutorial. You need to get 1. And number 2, the probability mass function ought to be non-negative everywhere for all x in the support of x. Okay, so these two look very much similar. However, I would like to caution you that property 1 implies that the probability mass function is less than equal to 1 for all x in the support of x. Definitely it must be less than 1, otherwise you cannot add up to 1. Okay, it must be less than 1. Do you agree? For the discrete case, the probability masses must all be less than equal to 1 and bigger than or equal to 0. You cannot have probability masses that are more than 1. Now, contrast and compare this to the PDF fx of a continuous random variable. By the way, for PMF of a discrete random variable, we always use P of x. For PDF, we always use f of x, no exceptions. If you write Px for a continuous random variable, you are very wrong. We don't want to do that. Okay, now let's contrast this to the PDF of a continuous random variable. Now, the fact of the matter is that fx of x can be larger than 1 for some x. Okay, it does not have to be less than or equal to 1 for all x. Okay. So we will see some examples of this later on. Okay. All that is needed is that this integral is equal to 1. Now, the fact of the matter is that if you have a non-negative function whose integral from minus infinity to plus infinity is equal to 1, that function need not be less than 1 all the time. Okay, so for example here, we have this particular function, probability density function. Okay, half 0. Then clearly, for this to be a probability density function, for this to add up or integrate up to 1, fxx here, this must be 2, so that the area here is 1. And so for some values of x, f of x is bigger than 1. So in particular here, f of x is equal to 2 for all x between 0 and 2. Okay. So that's one major difference compared to probability mass functions. Probability mass functions cannot have values 2. Okay, so this probability density function is a legitimate density function in which it is uniform on 0 to half. Okay, we'll see more uniform probability densities later on. Okay. So here is another property that it may be a bit hard to understand without some understanding of some calculus. All right, but all of you should have taken some calculus before. So So let me just say this, all right? If you don't understand, we can talk about it later, right? So let's consider just a small strip, the probability that X is between A and A plus delta. Now in math, right, that I also teach, delta is something very small, all right? So here's a picture. I'm interested in computing the probability that this particular random variable with a density f of x takes on a value between A and A plus delta. So this is our density, nice and smooth, right? Fx of u. And here's our A, and here is our close by neighbor A plus delta. What do you think this is? All right, so we have this here. Okay, so now this is by definition the area under this graph from A to A plus delta. So that is integral from A to A plus delta fx of u du. This is exact, this is an equality, exact equality. Now, if this function here, f of x, is very nice, in the sense it's continuous, okay? That's why it's called continuous random variable. Then, if delta is very small, this is approximately delta times f of a. Now, why is this so? You don't need to know any math for why this is so. You just look at the picture. Look at the red triangle here. What is this thing on the right-hand side here? This is the area of the rectangle with width delta and height fa. So the height is this height here. The height, it is fa. There's a height. So do you agree that the area of the rectangle is exactly delta times fa? That's the area of rectangle. This rectangle here, bounded by the purple lines. Okay, so the area of the exact area under the graph is the integral from A to A plus delta of the probability density function. But that is approximately, if this part, as you can see, is very nice, right? That doesn't fluctuate much. Then these two are almost the same. Do you agree? Common sense, right? Okay, Oliver's not here. Who can I call on? Prof. Isn't it x between 0 and, yes, thank you very much. Very, very sharp. Alvin G. Okay, now I call on Alvin G. Do you agree that, Alvin G, do you agree that the area is delta fa, which is approximately the integral from A to A plus delta of fx of u, just by the picture? So the exact area, sorry, let me use the red color. The exact area under the graph is integral A to A plus delta of fx of u du. However, the approximate area, which is the area of the rectangle, is equal to the weight, this is the base, and this is the height. So area of rectangle is base times height, I believe. Exactly. So, well, Alvin G said exactly what I said. All right. So do you agree? So that's one interpretation of the probability density function. Okay. So let me write this in English. Fx of A, all right, is the probability mass per unit length. A. All right. And actually this approximation here is better. This approximation is a better approximation as delta is small. Let's say it goes to 0. Okay, so this is some math thing. Never mind. Okay, so let us talk about some concrete things by doing some examples. Okay, example. Okay, let's consider a uniform random variable. This is motivated by the book. So you go into a casino and you spin the wheel of fortune. All right, so now at every point on the wheel, there is a certain number. All right, this number is 0.00. And at every point on the wheel, you get a real number from 0.0 all the way to 0.99999 and so on. So that's every, okay? So, so the wheel is continuous. The outcome of a spin of a wheel is a continuous random variable with values between 0 and 1. And since the probability of a certain number is 0, right? So whether I include 1 or not doesn't really matter. Okay, let's just say including 1. So now we spin the wheel, okay, using a very large force, and then we observe the outcome, x. And x is certainly a number between 0 and 1, maybe excluding, but never mind. Okay, so this is the outcome, and we like to understand some statistics of it. Now, I have one question. Here's a flashback. Okay, yeah. Fortunately, I don't have too many flashbacks. All right, so the fact is that any two subintervals of the same length have the same probability. So here I can draw the probability density function. It's fairly easy. So from 0 to 1, our probability density function, U, okay, is flat. It's very flat from 0 to 1. So it's uniformly distributed, you can say, okay? And in order for us to make this a probability density function, okay, we are going to have to choose the value C, all right? And I've already given it away as I said that C is equal to 1, but let's in fact compute that C is equal to 1. Okay, so f of x of u, right, is equal to C and 0 if x is between 0 and 1. So let's figure out the value of C. So the constant C can be derived based on the normalization constraint. And the normalization constraint says that if I integrate from minus infinity to infinity of the density, I must recover 1. All right. So let us try to use this to figure out the value of C, which you can see must be 1. All right. So this one here must be equal to 1. But this guy here on the left-hand side, all right, the density here is only non-zero in the interval 0 to 1. So if I integrate all the way from minus infinity to infinity, this is too much. Now, all the action happens between 0 and 1. So I can reduce it to this. But the value of fx of x or fx of u in the particular interval is C. So if I perform this integration, I get C times 1, and I need to equate this to 1. Now, clearly, from here, you get that C is equal to 1. And in fact, you can actually see that this is C equals to 1, because if you choose any number, then the integral under the curve, the area under the curve will not be 1. So you need to choose C equals to 1 here. Does that make sense? So if you choose C equals to 1, then the area here is equal to 1. So that's a very nice and simple random variable. Okay. So we can generalize this slightly, more generally. Okay, if x is uniform, is a uniform random variable on the interval AB. Now, whether I include the left side or the right side and or the right side is immaterial, okay, as I already mentioned. Then we have the density looks like this. The probability density function looks like this. Okay, you have A here and you have B there, and it is flat like this, flat. So we're going to try to figure out this value here. That is fx of u here. We're going to try to figure out this value C. Now, in order to make this, in order to make the area under the graph here equal to 1, now I think it's not so surprising that you need to take C to be a certain value as a function of A and B. And the exact function here, because the length of the base, right? The length here of the base here is B minus A, right? So in order for us to make the area of the red part equal to 1, I'm not going to perform this calculation, but you can see that C must be 1 over B minus A. Okay, so if you want me to perform this calculation, I can, but just eyeballing it, you can see that if I choose C to be this, then again, we recover that the area under the curve is equal to 1. If you choose C to be any other value, I'm sorry, it's not equal to 1. So that is some very benign example. Can you see that? Okay. Now let us try to do some not so benign example. Okay. All right. So let's see. This is a piecewise constant example, also shown in the book. This is not so straightforward already. Piecewise constant. Okay. So it is known that in this particular city, the probability of being sunny is 2/3. The probability of being rainy is 1/3. And if it is sunny, then Sean, let's say Sean, takes between 15 to 20 minutes to drive to NUS. But if it's rainy, because the conditions are not so good, then Sean has to take more time, right? So if it is unfortunately rainy, but Sean still wants to come to my lecture, then he will have to take on average slightly longer. Say it is rainy. Sean takes between 20 to 25 minutes, and the amount of time he takes within this interval is uniform. Uniform within each interval, be it the sunny interval or the rainy interval. Okay, so what does the probability density function look like? Okay, so we have fx of say u that is equal to constant 0. Okay, this corresponds to 15. X is u is between 15 and 20. Here is between 20 and 25. So the way to read these things is the following. You have this particular function. If the value u falls in this particular interval, then the function takes on this value c1. If u takes on values between 20 and 25, then the function takes on the value c2. So the picture is as follows, right? So our random variable x takes on values between 15 and 25 only. What does the probability density function look like? Well, here is 15, 20, 25. Okay, so it is certainly flat here. So here is certainly flat. And here is also certainly flat. And the value here, the height here is C1, and the height here is C2. And our job is to find these heights. Okay, our job is to find these heights. The way I've drawn it is the right way, okay? But let us try to find these heights. So we know that the probability that it is sunny is 2/3, right? So let's try to find C1. What is the probability that it's sunny? It's 2/3, but it can also be written as the integral from 15 to 20 of fx of u, because that's a sunny portion. Let me just write this. That's the sunny portion. And that is the rainy part. I'm integrating this part here. This should be 2/3 instead of 1. Okay, this part should be 2/3. That's what I'm doing in this calculation. So I have integral from 15 to 20, but it's flat, so it's C1 du. So this is 5 C1. Hopefully you understand. All right, so now dividing through by 5, we get C1 is 2 out of 15. So this C1 here is 2 out of 15. All right. Now we should now try to figure out what is C2. So C2 can be figured out by noticing that this part here contributes 1/3 probability. Okay, 1/3 probability. So let us try to consider the probability of it being rainy, which is 1/3. But it can be written in another way. Integrate from 20 to 25 of fx of u du. Now, in this particular interval from 0 to 25, fx takes on the value c2. Okay, this c2 comes from here. Look at this flatness here. We want this area here to be 1/3. Okay. So now here we have 5 C2. Where does this 5 come from? This 5 is the difference between these two numbers. Okay, here actually you need to do a little bit slower. So you know how to do this integration. Basically, you have C2U and then you 25, 20 like this, right? But so you have this 25 C2 minus 20 C2, that is 5 C2. Okay. So now by equating this 1/3 and this 5 C2, we get C2 is equal to 1 out of 15. And so that is the level here, 1 out of 15. So we have completely described the probability density function of this of Sean's travel time. And if it is rainy, then we will use this portion here. And if it's sunny, we'll use this portion here. All right. Does anyone have any questions here? One thing we need to check is that the area, the total area under this graph here should be equal to 1. And by eyeballing it, you should see that it's 1. Okay, Ken? So this corresponds to the sunny portion. And this corresponds to the rainy portion. Okay. Right. Okay, let us do one final example. Is it time? Yeah, that's minutes. You see, this person takes 15 to 20 minutes to go to drive to NUS. All right. So what they're saying is that this is the time. U is from 15 to 20 minutes. There should be some units here, but I dropped it. Okay. Thank you. All right. So you notice the following as well. All right. Here's an example. Now recall that for discrete random variables, x, they are accompanied by a probability mass function Pxx. All right, I've already mentioned that Pxx must be between 0 and 1. It cannot be very large. And the reason for this is that you sum up all the probability masses, they should be equal to 1. So if any one of the people or one of the probability masses is bigger than 1, then you bust the probability budget already. Okay. Now, this is very different, as I mentioned, in the continuous land, because the moral of this example is that the PDF can be arbitrarily large, can be very large. Arbitrarily large. Okay. So now let us look at this particular example. F of x, u, is equal to 1/2 square root u. Okay, this is too small. 1/2 square root u, excluding 0, including 1. This is quite important because PDS cannot be infinite. All right, if I exclude 0, none of these numbers is infinite. 0 else. So the picture is as follows. You have this, and you have this is 1, this is 0. And our fx of u is the following. And at 1, we are at half here. Right? Half. Because if I substitute u equals to 1 here, I get exactly half. Now, the support is only between 0 and 1, excluding 0, including 1. So it looks like this. It looks very much like this. Can you see? So that is our curve f of xu. Now, as you can see here, it holds that as u goes towards 0 plus. 0 plus means 0 on the right hand side, because 0 minus is this side here. As u goes towards 0 plus, that's what math people do. Then fx of u diverges to infinity because it becomes super large here. You are dividing essentially by something very, very small. You divide by something very small, then you get something very big, right? So this diverges up here. So the moral of the story is that PDF can be arbitrarily large. What do we have to check? We have to check that this is a legitimate PDF. That means that we have to check that its area under here is equal to 1. That we have not done yet, and we will do soon. So unlike for discrete random variables, the PMF cannot be arbitrarily large. It must be less than equal to 1. But for PDF, you can be very large here. Okay, so let's see. Let's check that this is a PDF. Is indeed a PDF. Now, what do we have to check? We have to check two properties. One is non-negativity and one is normalization. Non-negativity means that this whole thing is non-negative, cannot be negative, but obviously from the picture it's not negative, right? There's no need to check. Let's check that this is indeed a PDF. So let's integrate from 0 to 1, all right, of fx of u du. Now, this is the integral from 0 to 1 of 1 over 2 square u du. Now, if you remember how to integrate these sort of things, you bring out the half here, you integrate from this u to the minus half. You write it in this way first. At least that was how it was taught. I don't know how it's taught nowadays, but this is half. You put u to the power half divided by half. That is the way we integrate. So in the UK, right, people do this box thing. In the US, people do the line thing. All right, but whatever you do, as long as you do it correct, it's fine. Okay, this one. This one because hopefully you know how to integrate this. This cancels with this one here, and then you take 1 minus 0. I hope I'm not going too fast, but this is some integration thing. All right, and I'm not very good at integration. So the fact is that the area under the graph here, okay, the area under the graph here, even though it shoots up, the area here is finite. So the area here is equal to 1. Okay, even though this red line shoots up, but the area here is too small. So the accumulated area here is exactly 1. So this is a legitimate PDF. So before the break, what have we learned? We have learned that PDF is a way to describe a continuous random variable. If we want the random variable, we want the probability that the random variable is between A and B, then we integrate the PDF from A to B. Unlike probability mass functions, probability density functions can be very large. But no matter how large they are, the integral under the probability mass function, probability density function, must be equal to 1. So these are the main points that we want to take home from the first part of this lecture. All right. So I think now, okay, before that, I just want to make a final comment. So fx is a valid PDF because the integral equals to 1, but its value is very large. By very large, actually, there's a technical term for this in math. It's called unbounded. All right, but never mind. When u goes to 0 plus, all right, that means u approaches 0 from the right hand side. There's nothing to approach from the left hand side, so there's nothing to talk about. Okay, right. As I mentioned, now is a good time to take a short break. We will come back at 3 o'clock sharp. Okay, so we take a 12-minute break. Right. Thank you. The recording here. Before we start the next segment, please remind me to start recording. All right, so this continuous random variable has PDF given by f of x, which has some properties. All right, these properties are that it is non-negative and it must integrate to 1. All right, so we say that the expectation or mean or expected value, all these mean the same thing. All right, you will see all these terms. All right, the expectation, mean or expected value of a continuous random variable is given this same notation as that of a discrete random variable, expected value of x, with this strange e. All right, so that's my e. It's given by integral from minus infinity to infinity of x, f of x. Maybe I use u here. That's the variable of integration, du. So compare this to the discrete case when we have a probability mass function, then the expected value of x is equal to the sum over all possible values of x, px of x. Okay, so that is the for the discrete case. And in my tutorial, we have already done a lot on this. Okay, so that's the expectation. This is for discrete case, and this for the continuous case. So that is the definition. Here are just a few comments. All right, then we will do some examples. I need to do some theory first before I do some examples. Now, if I have that x is a continuous random variable, all right, then any real valued function of it, a function of x, is also a random variable. Now notice that I don't say that any real valued function of x is a continuous random variable, because it may not be a continuous random variable. Okay, so for example, if my real valued function of x is g of x, that generates a new random variable y. Okay, y can be very well discrete. Y can be discrete because my function could look like this. My function g could look like this. For example, g of x is a quantizer. Quantizer means, okay, let's say that the value x is positive or non-negative, then y takes on the value 1. If it is negative, y takes on the value 0. Y is gx. Okay, so now the support or the range of values of y, the range of values of that y can take on, the support of y is the set 0, 1. And this is different. This is different from the support of x. All right. So here is a pictorial example. Okay, let me see whether I can draw a nice picture or not. So our x looks like this. Our x PDF looks like this. Fx of x, x. Let's say it is uniform here between -1. All right, and it is uniform here from here to 3, 0. And say this 4. Let's make this number a bit better. This is 3/4. This height here. And this height here is cannot. This is not 3/4. Let's make this height 1/10. All right. And let's make this height half. Okay, so is this a legitimate PDF in the first place? No, this is terrible. Let me make this 5. I'm coming up with this example on the fly. Okay, so pardon me. Okay, let's consider this particular example. Now, is this a legitimate PDF in the first place? Yes, it is. All right. From the numbers I designed, f of x u du, you can check that this integrates to 1. Let's go from -infinity to infinity. This is from -1 to 0. You take the value half du plus 1/10 du from 0 to 5. So each one of these contributes half plus 5/10, which you can recognize is 1. So everything is good. Okay. So now this is a particular random variable x, and you're going to pass it through this function g of x, which is this what I call quantization or Heaviside step function if you wish. Then what happens? What is our probability mass function of y? Well, whenever x is positive, y takes on the value. Whenever x is positive, y takes on the value 1. So this is our probability mass function for y. Okay, so here we are transforming, right? So we have 1 and 0. Whenever x is non-negative here, that is this blue part here, then we map this to y equals to 1. Right? So this is here. And this has probability half. Now, whenever x is unfortunately negative, so here, then what happens here is that this gets mapped to 0. So I have another stump here at 0. And the heights of these two things are the same. It so happens to be the same. And the heights are all equal to half. So you can see that now if I pass it through this particular Heaviside step function, which is this function here, all right, if x is positive, I will map all these values to y equals to 1. And the mass here is basically 5/10, which is half, of course. And now if x is negative, okay, fine, then y will be exactly 0. Okay, so the probability mass function for y is shown here, which is equal to half if y is equal to 0, if y is equal to 1/2, and if y is neither 0 nor 1, then it's 0. So that's the probability mass function for y. As you can see, all right, I have a continuous random variable, but then after I transform it, it becomes a discrete random variable. Okay, so this is some example. Right. Anyone ask me any questions here? Okay. Right. So we can also compute the expected value of the random variable g of x, which is the expected value of the random variable y. Okay. Now, there are, as I mentioned before many times, there are two ways to do this. First, you go and, like me, figure out the distribution. Oh, sorry. Figure out the probability mass function of y. You do some work here. And then you can compute the expectation just by using the discrete expectation formula. But we don't have to do this. This is too laborious. We can go directly to the density of x and integrate against g of x, like this. So the fact that this is the same as if I go and find the density of y, and I use the expectation value of y, the fact that this is equal to this formula requires a small proof that I will not do. Okay. So now we can talk about other interesting functions like g of x equals to x to the power n. That leads us to expected value of g of x, which is equal to expected value of x to the power n. And this expression looks like x to the n fxx dx. Now, this is the same as, sometimes I use u here because I don't like too many x's. But you should be comfortable looking at both of them because the u and the x inside here, they are just dummy variables. X here, they're dummy. You can use anything you want. I just want to distinguish from x sometimes because there are too many x's here. So this function here has a special name. This is called the nth moment of the random variable x, of the continuous random variable x. It's called moment. Okay, for some reason it's called moment. I also don't know why. Okay, now once you have the moments, okay, then you can talk about the variance, just like what we talked about last time for discrete random variables. So the discussion here is kind of quick because we have already seen this sort of thing before. The variance of x has two different formulas. One is the following: expectation value of x minus the expectation value of x quantity squared. Okay, that is the standard formula. But a little bit of manipulation shows you that this is equal to expectation value of x squared. So the second moment is called the second moment minus the first moment quantity squared, right? So that is the variance. Usually we use this formula to compute the variance. Usually this is much easier because usually before we compute the variance, we compute the mean already. So we have the expectation value of x. So we just need to compute the second moment. All right, the fact that this is equal to this follows from the same lines as the discrete case. Okay, follows from the same argument as for the discrete case. So let me see whether we should revise that. Yeah, why don't we just do that? So starting. So what am I trying to prove now? I'm trying to prove this equivalence, okay? Starting from star, we have that the star here is this expression. I'm just trying to show you this, okay? Right, you can do it on your own. This is the integral of x minus expectation value of x quantity squared fx of x dx. Okay, so if I don't do minus infinity to infinity, that's what I mean, all right? I'm not going to put the infinity very soon. So we can expand the inside. Minus infinity to infinity, x squared minus 2x expectation value of x plus expectation value of x quantity squared fxx dx. So because now the next step is integration is linear, all right? So the fact that integration is linear is very deep result in mathematics actually. So you have x squared fx of x. This is where the second moment comes in. You can see this is the second moment part. And then we have minus the expectation value of x can come out of the integral. you have to integrate 2x. The 2 can also come out. Let's make it more convenient. fx dx plus expectation value of x all squared. So this part here comes out of the integral, it comes here. And you have the integral of fx x dx. Okay, so this 2 expectation value of x, right? This 2 and this expectation value of x comes out here. All right, so all the remaining stuff is inside the integral. All right, so now what we have is the following. Okay, so let me not write so much. This is equal to, all right, this part here has a name. What is it? Liao Xue. This part here has a name. Now I know one person. I know one person saw something. Just now you send some email. This part that I underline has a name. It's called the. You see the integral of, maybe I will put in this. Expectation of x, yes. Right? So we have the expectation value of x here. Okay, now I know that person who answered me is not Mr. Saw. So Mr. Saw, what is this? Someone sent me an email now. What's his name? Oh, Saw Wicket. Yes, Saw Wicket. What is this thing here? I'm integrating from minus infinity to infinity of the probability density function. Exactly 1. Okay. So now, thank you very much. The first thing is the second moment. And now we have 2 expectation value of x. But you have expectation value of x, so you square, right? Plus expectation value of x squared times 1. Because we get it so. So now we have expectation value of x squared minus expectation value of x quantity squared. Okay, I think it's better to put more brackets here. Okay, otherwise it doesn't look good. Okay, so as you can see here, this is the whole proof. It's not very difficult, but I don't expect you to do this. You don't need to do this. Okay. Right. The fact that the variance is this expression here, it's a square, it's an expectation of the square of something. All right, means that the variance of x is non-negative. Always variance of x is non-negative. Always. And because variance of x is equal to the second moment minus the first moment, quantity squared, this is non-negative. This actually means that the first moment squared is less than equal to the second moment. Okay, but this is just some small relationship. I'm not sure whether we will use this or not. And this has a name also. This is called the Cauchy-Schwarz inequality. Okay, in some math thing. Okay. So here are some very basic relations. Then we'll do some examples. We need to go through all these things. Linearity of expectation holds. Linearity of expectation. So if I have x, y, 2 continuous random variables, and I have a A, B, C, which are all scalars, they are not random, then oftentimes I would like to figure out what is expectation value of AX plus BY plus C. Now that's not very difficult. It's expectation value of X times A plus B expectation value of Y plus C. Okay, so this you can prove. I'm not going to do this already. Okay, so this one you can write out by yourself and you should know how to do this. All right, this is simple enough. But what is not so simple is the following, right? Maybe it's not so obvious. All right, let X and Y be independent, continuous random variables. Okay. Now, I have not talked about what is independent for continuous random variables yet. I owe you that. But can you just believe me that independent means the same as what it was for the discrete case? And we are interested in the variance of the linear combination or the affine combination AX plus BY plus C. So that's what we are interested in. Now, if they're independent, last time we already showed that for the discrete case, this is equal to A squared variance of X plus B squared variance of Y. And this formula carries through to the continuous case, no problem. I'm not going to prove this already. Okay. So we can just accept this. So now in the remaining part, right, I want to do some calculations and some examples. Okay. Any questions here? We have already seen all these results for the discrete case, so I'm not going to belabor the point. Okay. So if there are no questions, let me talk about some examples. Okay, so these some examples require a little bit of algebra, so be prepared. So let's figure out the mean and the variance of a uniform random variable. Okay, so our uniform random variable, we write x distributed as uniform AB. You don't really need to worry about what this notation is, but you need to know what is a uniform random variable. So it takes on value 1 over b minus a when x is between a and b, and otherwise nothing. So the picture is as follows. So you have this a here, b there, and we have this flat thing here, and the height here is, as I calculated just now, 1 over b minus a. That is your fx of u. I toggle between u and x. You should be comfortable with that. Okay, so intuitively, as I already mentioned last time, what is the mean or the expectation value? It is the center of gravity, right? So if I put like a sharp knife here in the middle, then this whole density balances, right? As you can imagine, it balances. It will not topple over. So that is where the center of gravity or the expectation value is at the center of mass. But let us see whether the math actually works out, okay? So let's try to find the expectation value of x. Let's plug into the formula. Okay, all the excitement only happens between a and b, so I can restrict myself to this. X, fx of x dx. That's the expectation value. So we have x is 1 over b minus a dx. So 1 over b minus a is a constant. It can be brought outside. And I'm integrating this polynomial, right? X dx. So I hope that you understand how to integrate this from some introductory calculus class. BA, like this. Right, so you need to know how to do these sort of things before you take this class. So I assume that you know how to do this. So you have 1 over b minus a, and now you have to do b squared minus a squared over 2. Now, I don't know whether you remember or not, but I also can forget about these things. B squared minus a squared is b minus ab plus a. All right. So these are some basic identities. I think you call them identities in school. This can cancel with this. And so you basically recover that the average or the mean or the expectation value is a plus b over 2, which is what you intuitively expect this to be, a plus b over 2, which is the expectation value of x. It's the center of gravity. Okay, does everyone understand my beautiful algebra? So everyone understands my integration? Now, later on, we're going to do much more challenging integration. We need to integrate by parts later on. I don't know whether people know how to do integration by parts or not, but I also sometimes forget. Never mind, we can try to recall together. So now let me try to compute the variance. This again requires some delicate calculation. Okay, but it's described in the book and you should know how to do this. So as I mentioned for the variance, right, it's better to get your hands on the second moment. Let's try to get our hands on the second moment. So that is integral of a to b, x squared fx of x dx. But this fx of x is constant. It's 1 over b minus a and x squared dx. All right, so because fx is constant on this interval, so I can bring it outside, and it's 1 over b minus a. So now we have 1 over b minus a. Here we are going to integrate x cubed over 3. Oh gosh, ba. So now what we have is b cubed minus a cubed over 3b minus a. Okay, now from here on, right, it's either you know it or you don't know it. These two events are disjoint. Either you know the next fact or you don't know the next fact. Most of the time, we don't know because we don't do this every day. At least I don't do this every day. But the fact of the matter is b cubed minus a cubed is b minus a, b squared plus ab plus a squared. Yep, this is the right direction. You can do long multiplication out and you'll notice that everything cancels beautifully. Okay, so now if you divide this guy by this guy, you recover this guy. So that's what we will recover here. B squared plus AB plus A squared over 3. So either you know this or you don't know this, but I'm telling you that this is an identity. Okay, so you can go and verify this. How do you verify this? You multiply this throughout. Okay, and you see a lot of things will cancel. All right, so now after you're all said and done, the variance is expectation value of x squared minus expectation value of x quantity squared. So what we have is we need to do this one here. We need to copy this properly, put here. And then we need to copy this and then put here. And we need to subtract this quantity squared. And then we need to go through a bunch of algebra that I will not go through. Massage this until it looks beautiful, that I will not do. It's b minus a squared over 12. Okay, so that is the variance. That's how we calculate the variance. We calculate the first moment, which is the expectation value. Then we calculate the second moment, and then take the second moment minus the first moment quantity squared. And we are good. And if we are very careful, meticulous with algebra, not like your professor, then you will calculate this correctly. If you are very lazy, you can just look up this thing from Wikipedia. All the distributions are tabulated. What is their mean? What is their variance? What is their mode? What is their median? What is their so on and so forth? It's all in Wikipedia. So, but we have to do this for character building our own character. Okay, understand? Okay. So the next thing I want to do and is to introduce you to the world of Okay, any questions on this calculation? I don't want to do all the very small little things. Okay, I want to focus on the big ideas. Okay, the next random variable or continuous random variable I want to play with is called the exponential random variable. And it has the density given by the following. Fx of x is lambda e to the minus lambda x when x is non-negative, and if x is negative, you get 0. And the picture is as follows. Okay, so you have fxx here, and this x, and nothing happens on the left-hand side. It's a non-negative random variable, and here lambda, and here this decays exponential. Okay, so this curve here is given by lambda e to the minus lambda x. Okay, so you might think, right? Why do we even create all these strange random variables? What is the purpose of this? Why do we even care? Is it because we want you to suffer in doing math and we create all these random variables that are kind of artificial? No, because they are applicable in real life. And so I want to show you some example of when we use exponential random variables. How to share screen. Here is my motivation for exponential random variables. Okay. Share. Okay. Here. So we are interested in the arrival times of goals in football games. Are the arrival times of goals exponential random variables? Okay, so we are going to do an experiment. Now, as I already told you, the exponential random variable has this particular probability mass function. It looks like this for different lambdas. Okay, so the formula is above, and I wrote it down on my handwritten notes as well. So the inter-arrival times of this thing called the Poisson process, which I teach, okay, in some other class, is the IID process xi, where each xi is an exponential random variable. You don't need to know what's IID. You don't need to know what's process. You just need to know that the arrival times follow exponential random variables. So it has this probability density function. So we want to see whether this is a good model. So before you were born, there was the World Cup. All right. So we are going to focus on the 232 World Cup or soccer games from 1990 to 2002, when you were not born yet. Okay, so in the first game in the 1990 World Cup held in Italy, Cameroon scored a goal against the reigning champions Argentina in the 67th minute. In the second game, Romania scored 2 goals against the former Soviet Union at the 42nd and the 57th minutes. Okay, the times to these goals are 90 minus 67. Every football game is 90 minutes, okay? 90 minus 67 plus 42. So that's the interval between the first goal scored and the second, if you stack the games back to back. And then 15, which is 57 minus 42. So the picture is as follows. All right, so this is the first game between Cameroon and Argentina, 90 minutes, and there was a goal here at the 67th minute. Then I wait for 65 minutes for the second goal, which happened in the second game at the 42nd minute. Then I only have to wait 15 minutes for the third goal. So that's the process of the arrival of the goals. Now, for the exponential random variable, very soon we are going to prove, or we're going to calculate, let's say we calculate, that the mean and the standard deviation coincide. So the mean is 1 over lambda. The variance is 1 over lambda squared. We are going to show this later on through integration by parts. A bit painful. Okay, so the standard deviation is square root of the variance, hopefully you know. So the mean and the standard deviation coincide. So empirically, if you look at all the 232 goals, right, you look at their inter-arrival times. The first few inter-arrival times are, okay, the first one is 67 minutes, the second one is 65, the third one is 50. You look at all these numbers, okay? Then you go and compute their empirical mean. That means you go and there's average, okay? You get 36.25 minutes. Then you go and compute their empirical standard deviation. Empirical standard deviation means you just pretend that the data is what it is. You compute the variance, you estimate the variance, and then you take square root, you estimate the standard deviation. And then you see, oh, well, these two numbers are almost the same. So that actually corroborates that the inter-arrival times follow exponential random variable, because exponential random variable is one in which the standard deviation and the mean coincide, since you square root this. You square root this thing. Okay, so the lambda here, all right, is approximately 574, which is the total number of goals, divided by the total number of games. Okay, and this compare well to the theoretical explanation. So the inter-arrival times actually is a reasonable model. The exponential distribution is actually a reasonable model for the inter-arrival times of goals, as you can see from the data. Now, there's this other property called memorylessness, okay, that is a bit too much for us to go through, but the exponential random variable that we are going to calculate a few things is also a memoryless random variable. And if you look at the times between the goals, you can actually verify some property about memorylessness, okay? So the inter-arrival times of goals are also memoryless, and this is corroborated by the data. These numbers here are almost the same. So the exponential random variable is useful. We are not just coming up with it to make your life difficult for the exam, but it's actually a useful model for the arrivals of customers into your shop and arrivals of goals in a football game. All right, so you can look at all these things. I made this some slides, okay? Anyway, don't you think it's interesting? Amusing, right? Come on. So this process is actually very interesting, and it can be modeled using exponential random variables. So it's worth studying this random variable here. So we want to show now that actually 3 things. We're going to calculate, number 1, that the exponential PDF is a valid PDF. Number 2, we want to show that its expectation is 1 over lambda. And number 3, we want to show that the variance of x is 1 over lambda squared, so that the standard deviation of x is equal to 1 over lambda, which is same as the mean. Okay. Okay. The golf question is not exactly memorylessness, but I can see where you're coming from. Problem 2.43 is about memorylessness of the geometric a random variable. Okay, you can go and look at that. I wanted to do that, but I don't think I have time. I need to do this integration by parts. Okay, so now we want to show these three things. Okay, so this is a valid PMF, a PDF. So we need to check that the area under this graph here is 1. Okay, so we are going to check that. Check. Okay, so we have to do some integration. All right, if you like integration, this is a fun exercise for you. If you don't, this is very painful. All right, fx of u du. Let's check this. So this is lambda e to the minus lambda x or u du. So exponentials are usually very easy to integrate. And so you can integrate this thing. You have minus e to the minus lambda u. You put it infinity and 0. Okay, so one of the lambdas gets killed with another lambda that is in the front. Okay, so I don't know how you learn these things, but I learned it this way. And this is 1. All right, because you put in infinity, you get 0. You put in 0, you get 1. And the minus and minus cancel. So that's the way I do it. So this is good. We integrate to 1. The area under the graph is equal to 1. Area under here is verified to be equal to 1. Okay, so now we want to compute the expectation, which requires integration by parts. I don't know whether you remember. The variance was still. Okay, so let's compute the expectation. We need to do this. You integrate from 0 to infinity u of fx of u du. And the reason why we integrate from 0 to infinity is because the support is only in this range here. There's nothing happening here. All right, so let's do it. Integrate from 0 to infinity u lambda e to the minus lambda u du. Okay, so I don't know how you learn integration by parts. I don't know whether people learn it the same way these days, but in my good old time, you do this. U minus e to the minus lambda u infinity 0. This one here minus e to the minus lambda u du. Okay, the first part goes to 0. The second part is this e to the minus lambda u du. And this one here is, I know either I'm going too fast or I'm going too slow. But if I'm going too fast means your integration is lacking. If I'm going too slow means your integration is good. All right, so this is going to be minus 1 over lambda e to the minus lambda u from 0 to infinity, which is 1 over lambda. Okay, so this part here, right, from here transition to here is something called integration by parts. Okay, so integration by parts is something that must be ingrained inside you if you do these sort of things. But if you don't, then you need to know what is happening. Okay. All right, so this is just some integration. Good. Very good. It's a bit painful, but we have to do it. So the expectation I verified to be 1 over lambda. Okay, so we are all set. This is expectation. So if you don't know what I'm doing, I can explain to you integration by parts, but not in this lecture. All right. So I can just say how I remember this. All right. We find something to integrate, like this one we integrate, and we keep this here. We keep this here, we integrate this, we get minus e to the minus lambda u. We put down the limits. And then we put down the integral that we have and you will differentiate this one. Okay, so that's the way I remember. A bit faster. Okay, but then we get to this point and then this is regular integration. All right, so we have figured out the expectation. Now let's figure out the variance. Okay, so expectation value of x squared. Because when we want the variance, right, we need to figure out the second moment. U squared fx of u du. Okay, so now we have the following: u squared lambda e to the minus lambda u du. Right, so this calls for double integration by parts, but we don't have to do double. If you are very careful, you don't have to do double because you can do a shortcut. Now you see here, we are going to integrate this and we're going to differentiate this. Right, so once we integrate this, we have u squared minus e to the minus lambda u infinity 0 minus, put down the integral, minus e to the minus lambda u multiplied by differentiate 2u. Okay, so this, the first term always goes away and you are left with 0 to integrate to 0 to infinity u e to the minus lambda u du. And actually you have already done this one here. You have already done this. And basically from the previous calculation that this is equal to this, we can readjust a few things and we can see that this is 2 over lambda squared. There's no need to do any more work. Because with this additional lambda here, we have 1 over lambda squared. So we can divide throughout by lambda. And then we have that integral of u, e to the minus lambda u is actually 1 over lambda squared. So if you multiply by 2 here, you have this 2 over lambda squared. Okay, my calculus is only this much. So now you can compute the variance, which is the expected value of x squared minus the expected value of x quantity squared, which is 2 over lambda squared minus 1 over lambda quantity squared, which is 1 over lambda squared. This is what we sought to prove, or calculate, not prove. All right, the variance of x is 1 over lambda squared. Now, if you find that any of this is a bit challenging, okay, that means your integration is not very good, okay, but never mind. This class is not, I'm not going to teach you, I'm not going to test you on very, very difficult integration, okay, because the probability concepts are more important. All right, so this is all the calculation I've done to compute the variance. Now let's actually use this to do something, okay. Now, this question is not in the book. I came out with it on my own, but it concerns exponential random variables. You can choose to copy or you can choose not to copy. It's fine because I will make these notes available anyway. Okay. The arrival of goals in a game of football, is an exponential random variable with mean 10 minutes. Okay, so my question is find the probability that the first goal is scored between the 40th and 45th minute. Okay, so there are a few things to unravel in this question, all right? First and foremost, we know that we are dealing with continuous exponential random variables and the mean is 10 minutes. So now I want to compute the probability that the first goal is between the 40th and the 45th minute. So we have this timeline here, that is 0, 40, 45th. So our first goal must lie here. There must be 0 goals from here to here, 0. Okay, and there must be 1 here. The first goal is scored between the 40th and 45th minute. So that's the picture, all right? So there are a few things to unravel from this question. The first is, now, let x be the random variable that characterizes the time the first goal is scored. Okay, now I know that x is exponential random variable. And I know that the expectation value of x is equal to 10 minutes. Right? So from our very laborious calculation here, we know that the expectation is 1 over lambda. So I want to get my hands on lambda. Okay? So that means that, well, expectation value of x is equal to 1 over lambda. So lambda is 1 over 10. Okay? 1 over 10 arrivals per minute. Actually, that's more precise, but never mind. So what we are interested in is the probability that the first goal is scored between the 40th and the 45th minute. Okay, that's my question. Okay, actually we did something like this in the tutorial just now. I don't know whether you remember. But this we can compute the probability that x is bigger than 40, bigger than or equal to 40, minus the probability that x is bigger than 45. Do you understand why? Okay, this is something that we need to understand. So I'm interested in the probability of this interval here. Okay, now that is the probability of everything from 40 onwards like this, minus the probability of the arrival being more than 45. right? Then I recover this interval here. Understand? Now you get it. Perfect. Very good. So we need to figure out these people here. Okay, so these are exponential random variables. So I need to integrate from 40 to infinity of the exponential PDF. The exponential PDF is lambda e to the minus lambda u, and the lambda is 1 over 10 e to the minus 1 over 10 u du minus integral from 45 to infinity 1 over 10 e to the minus 1 over 10 u du. And the fact that this is not included here is immaterial, as I mentioned at the start of the lecture. Immaterial. Immaterial means don't care. Okay, so we're going to perform this integration here, and we have minus e to the minus 1 over 10 u, plug in infinity 40, minus e to the minus 10 u, plug in infinity 45. And after you're all said and done, okay, let me see. After you're all said and done, you have e to the minus 4 minus e to the minus 45 over 10, 4.5, okay? Okay, so this is whatever number it is. All right, I didn't press my calculator. Okay, but this number is positive. Okay, as probabilities must be positive. So that's the way we actually unravel the question. This is a slightly different question from the book, because I thought I want a question that ties in with my example. So the rivals of goals in a game is an exponential random variable with a certain mean. From the mean, you can actually deduce what's the lambda. Okay, the lambda is deduced based on this relation here. Okay, then we solve the equation here. Then I want to find the probability that the first goal is scored between the 40th and the 45th minute. So there's no goal here. All right. So we basically use this relation, okay, that I talked about in the tutorial just now. Some people do not know what's happening, but fortunately David is enlightened now. So now we have to integrate the PDF from 40 all the way to infinity, because that's what is represented here. Here 45 to infinity. And then after some algebra that I'm not going to describe, you get some answer. Okay? And this is where I will stop today. I don't need to use up all the time. And I want to wish you a very happy recess week to do my homework. And if you don't know how to do it, it's okay. You can always ask me. Cho Yu says that he's going to fail, but I don't think so. If he's going to fail, that means that there's only one reason. That's I'm a bad teacher. Are you implying that? Okay, I don't think so. Okay, what are these people saying? Especially 5B and beyond. What is 5B? Homework. You can ask me. You can ask me. Okay. Anyway, let's call it a day. And I can answer questions from the people here. Okay. Bye bye. The Zoom people. Bye bye. You want to the Zoom people, right? Some of the people in this audience, they have collected your thing, your quiz for you, so you can get it from them. Okay. Bye bye. Bye. I'm going to log off here. Okay. Yes.